In this session, we are going to discuss a very interesting problem related to axial rods in tension and compression. Um, Somewhat a non-trivial problem of how to find a rod of equal stress. What that means is that if you have a rod like the one I'm showing here, subjected to its own self-weight, we would like to find a distribution of cross-sectional area along the length such that the stress at any cross-section is exactly the same. So the stress up here, the stress here, the stress at any cross-section along the height is exactly the same. Now the interesting part of this problem is that, as you cut at any distance x from the free end, the total weight of the part of the rod that is exerting a tension force at that section is an integral that depends on the variation of the cross-sectional area up to that point. So it would be the axial force, n as a function of x, would be the integral from 0 to x of rho g a x prime dx prime. So as you change the area, you also change the weight. So it becomes a somewhat of a non-trivial problem to find out how does the area need to change across the length in order to keep the stress constant, right? So the axial force is changing as a function of x, the area is changing as a function of x, but for every value of x, n, the force, divided by the cross-sectional area, is a constant. So there are a couple of ways to approach this problem. The simplest way that I have found is to look at the differential equilibrium of any slice of this rod along the height. So if we take equilibrium of a single slice of thickness dx, we will find that below it has an axial force which we're going to call nx, and above here it has an axial force which is nx plus the increment in n, right, due to the self-weight of that slice, which is rho g a as a function of x times dx. So simply setting sum of forces equal to 0, we find that dn is equal to rho g a dx. This a is a function of x, and this n is a function of x. So this is a key equation here. It basically tells you that the increment in axial force is related to the density, the gravity, and the area of that cross-section times dx. On the other hand, based on this equation here, we can write that area as a function of x times the stress, which is a constant, equals to nx. If we take the derivatives of both sides, we find that dA dx times sigma naught is dn dx. So this is taking derivatives of both sides. And we can see here we have dn on both of these equations. So we simply need to divide by dx on both sides, and we find that dn dx. So we can set these two equations equal to each other, because they both have dn dx. If we do that, we find that rho g a as a function of x equals sigma naught dA dx. And solving here, we have rho g divided by sigma naught times dx equals to dA over A. Integrating both sides, and we can call this here, this is a constant, by the way, because rho is constant, g is constant, and the stress at every cross section is constant by definition. So we're going to call that alpha dx equals to dA over A. And then integrating both sides, we simply find that we have here alpha x, and then we have here log of A. All of this plus a arbitrary constant of integration. If we take the exponential of both sides and use the rule for sums of exponentials, we find that A as a function of x equals E equals a constant times E times alpha times x. You can verify this equation very simply, because if you take derivatives of both sides, you will find dA dx equals to alpha dx, which is what we have found here. So what this equation tells you is that the variation of the area, the cross-sectional area that is necessary in order to keep the stress constant as a function of x is an exponential. So, and that exponential has a constant which is proportional to the density and to gravity, and inversely proportional to the desired stress that you want to maintain constant. So again, the variation in the area is a function of x, necessary in order to achieve constant stress